So hello and welcome to week 4 of the NPTEL noc23-ma14 Algebra-II course. So I am one of the TAs for this course. My name is Shubhajit Das. This is my email ID, and as we do every week, we'll be solving problems from this week's assignment. So I do hope that you have also been attending Ajay Prajapati's sessions as well. So yeah, so let's start. So this week you have studied about separability, normal extensions, etc., etc. So we'll be doing problems based on that. Okay, so let us start solving the problems one by one. So problem one. Okay, so let us take eta to be equal to e to the power 2 pi I by 5. Now we need to choose all the correct options. So choose all the correct options. So option A is Q adjoined with eta is a splitting field of x to the power 4 plus x cube plus x square plus x plus 1. B is Q adjoined with eta is a splitting field of x to the power 5 minus 1. Option C is Q adjoined with eta is a normal extension and option D is the degree of Q adjoined with eta over Q is exactly 5. So you need to figure out which of these options are correct. Okay. So let us see the solution of this. So eta here is a primitive fifth root of unity, right? Which means that if we look at all the fifth roots of unity, then eta that clearly form. If we look at all the fifth roots of unity in over Q, then that forms a group. It's a cyclic group. It's a cyclic group, and eta is a generator of that group, right? Yeah. Okay. So now option A here is correct because the polynomial x to the power 4 plus x cube plus x square plus x plus 1, this is precisely 5 of x, which is, in other words, this is the fifth cyclotomic polynomial. This is the fifth cyclotomic polynomial, right? Which means that this is just the polynomial over Q whose roots are precisely all the primitive fifth roots of unity. Now the number of primitive fifth roots of unity will precisely be the number of generators of the cyclic group Z5, right? Which is phi of 5, Euler's phi function applied on 5, which is 4, which suggests that the fifth cyclotomic polynomial should have degree exactly 4. Now now observe that x to the power 5 minus 1 is x minus 1 times x to the power 4 plus x cube plus x plus x plus 1, which means that the roots of x to the power, and we know that the roots of roots are precisely e to the power 2 pi I by 5, e to the power 4 pi I by 5, e to the power 6 pi I by 5, e to the power 8 pi I by 5, and e to the power and 1, right? Now 1 clearly is a root of this, 1 is a root of x minus 1, which basically means that the other yeah, which basically means that the other 4 roots are for this particular polynomial, right? X to the power 4 plus x cube plus x square plus x plus 1, which implies that e to the power 2 pi I by 5 in particular is a root of, I mean, not just e to the power 2 pi I by 5, every one of them, e to the power 2 pi I by 5, e to the power 4 pi I by 5, e to the power 6 pi I by 5, and e to the power 8 pi I by 5. All these 4 are roots of the other polynomial, other factor, are roots of x to the power 4 plus x cube plus x square plus x plus 1 x. And what this precisely means in other words is that q adjoined with e to the power 2 pi I by 5 is a splitting field. Over q of the polynomial x to the power 4 plus x cube plus x square plus x plus 1. Okay, so indeed option A is correct, right? So to obtain a splitting field, as I have explained previously many times, to obtain a splitting field of a polynomial, what you do is you just look at the base field and adjoin with the base field all the roots of the polynomial, right? So there is some large field which contains roots of this, some large extension of the base field which contains all the roots of this given polynomial. You just adjoin with the base field those roots, and the particular subfield that we obtain, that is an extension of the base field, and that extension is a root of the polynomial. I mean, that extension is a splitting field over the base field of the given polynomial. So option A is certainly correct. And in fact, option B is correct as well. This is again obvious, right? That q eta is also a splitting field of x to the power 5 minus 1, right? Q eta is a splitting field of the polynomial x to the power 4 plus x cube plus x square plus x plus 1. And you know, if you multiply x minus 1 with that, you get this, you get the polynomial x to the power 5 minus 1, which is precisely the polynomial which contains all the primitive, which contains, I mean, whose roots are all the fifth roots of unity, right? So option B is again correct, because to obtain a splitting field of this polynomial over q, you just adjoin with q all the roots of this polynomial, and e to the power 2 pi I by 5 in particular contains, I mean, q adjoined with e to the power 2 pi I by 5 contains all the other roots as well. It contains 1, it contains e to the power 4 pi I by 5, e to the power 6 pi I by 5, e to the power 8 pi I by 5. Okay. Indeed, option B is also correct, that q eta is a splitting field of x to the power 5 minus 1. Now option C is also correct. C is correct. Because q adjoined with e to the power 2 pi I by 5, as we just saw, that q adjoined with e to the power 2 pi I by 5 is a splitting field. Is a splitting field of some polynomial, over q. This is a splitting field of some polynomial over q, and hence every splitting field is always a normal extension, right? Which implies that q adjoined with e to the power 2 pi I by 5 is a normal extension of q. This is always true, right? Regardless of whatever extension you are taking, if you take any, so suppose you take a polynomial over some given field, and assume that you look at its splitting field. Let's suppose fx is a polynomial, and over some field capital F, and you take a splitting field E over F of this polynomial. Then for any irreducible polynomial gx in the base, over the base field, that is gx in fx, that has some root in the splitting field, it will have all its roots in the splitting field, right? Which is precisely what the definition of a normal extension is. An extension E over F is called normal if so an extension E over F is called normal if it is algebraic, and for any irreducible polynomial over the base field which has a root in the extension, all its roots will be in the extension. That is, any polynomial, any irreducible polynomial over the base field that has a root in the extension splits completely over the extension into a product of linear factor. Yeah. So option D is false. Option D, what does option D says? Statement D says that Q adjoined with e to the power 2 pi I by 5 as an extension of Q has degree exactly 5. Now tell me something. What do you know about this? What do you know about the degree of an extension of this form, Fa over F? This is some Fa. If you take a field and adjoin if you take a field, take an extension of the field, take an element in the extension, and if you consider the subfield which is obtained by adjoining the element to this base field, that is, if you take F and if you take an element A in some extension of F, and if you consider F adjoined with A, this is something called a simple extension, right? What do you know about the degree of this extension? What can you say about the degree of this extension? Firstly, we know that this extension is a finite extension if and only if A is algebraic over F, and in fact, if that is the case, if indeed A is algebraic over F, then the degree of this extension will be equal to the degree of the minimal polynomial of A over F, right? This is what we know. Now e to the power 2 pi I by 5, we just need to find out the minimal polynomial of e to the power 2 pi I by 5 over Q, right? Now e to the power 2 pi I by 5, observe that it satisfies two polynomials, right? It satisfies both x to the power 4 plus x cube plus x squared plus x plus 1, as well as it satisfies x to the power 5 minus 1. That is, it satisfies both these two non-zero polynomials. That is, it is a root of both these two non-zero polynomials. But we want the polynomial with minimal degree, right? So it certainly can't be 5, right? Because we already found a polynomial of degree 4 which which has this element as a root, right? So a polynomial of degree 5 cannot be a root. Is it clear? We already have found a polynomial of degree 4 which has this element as a root. So certainly the degree can't be 5, right? The degree has to be less than equal to 4. In fact, the degree will exactly be equal to 4. So this is so check that this degree is exactly equal to 4, because x to the power 4 plus x cube plus x squared plus x plus 1. First of all, this is a monic polynomial, and secondly, x is this is in fact the minimal polynomial, is the minimal polynomial of e to the power 2 pi I over 5 over Q. You need to check this, that this is the minimal polynomial, and the way to see this is very easy. Just check that. So the hint is so you just need to check that this polynomial is irreducible over Q, right? Because you know that minimal polynomials have various ways in which you can define minimal polynomials, right? Firstly, you can define a minimal polynomial, the minimal polynomial of an element over some base field, to be the polynomial of smallest positive degree or least positive degree which has this element as a root. Or you can also define it, let's say like this, that it's a monic irreducible polynomial which has that particular element as a root. Any way will work, right? So use Eisenstein. This is a exercise in basic ring theory. Use Eisenstein's criterion to show that x to the power 4 plus x cube plus x squared plus x plus 1 is irreducible over Q. And once you check that this is irreducible, this polynomial is irreducible over Q, you already know that e to the power 2 pi by 5 is a root of this polynomial. You are done. This will be the minimal polynomial, and hence the degree of this extension will be 4. So in any case, D can't be correct. This can't be 5. Okay. So if you have any questions, you can ask me. Yes. 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 Uh, um, what kind of I mean, what level are you currently in? I mean, what exactly are you studying? Yeah, so e to the power 2 pi I by 5 is just cos 2 pi I by 5 plus I sin 2 pi I by 5, right? Theorem. I mean, e to the power exponent e to the power this is equal to this. You can show using complex analysis or something of that sort. But these two are equal. These two are the same thing. So if you are having problems with this notation, this is not just a notation. This is a number. E to the power z has a meaning in complex analysis. But if you have problems with this, you can just think of this as cos 2 pi by 5 plus I sin 2 pi by 5. The point is that it's this, whatever this is just a fifth root of unity. That is, it is a root of this polynomial, and not only it is just a root of this polynomial, it is a primitive fifth root of unity, which means that it's a fifth root of unity and no smaller. I mean, it's not a root of unity for, I mean, it's a fifth root of unity, but it's not an nth root of unity for any n less than 5 greater than equal to 1. Okay. Yeah. What do you mean by significance? No, e to the power 2 pi by 5 here just has been thought. I mean, see, after all, everything you do in abstract algebra, you just play around with symbols and you have some operations, right? This is the basic of. I mean, this is what you do in abstract algebra, right? You all. So e to the power 2 pi by 5, you can think of it as a symbol. The point is that it denotes a fifth root of unity. It denotes the primitive fifth root of unity. So if you look at x to the power 5 minus 1 in qx, if you look at this polynomial, you know that every polynomial over every non-constant polynomial over any field has a splitting field, right? Splitting fields exist, and not only do they exist, they are unique up to isomorphism. So if you look at x to the power 5 minus 1 over q, now this has all its roots in C, right? If you look at all its roots in C, it has exactly 5 roots. This is something called a separable polynomial. I believe you guys have studied separability this week. So this is a separable polynomial. This polynomial has only simple roots, right? Which means that all its roots are distinct. So it has 5 distinct roots in C, and those roots, if you list them, those are 1 e to the power 2 pi I by 5, e to the power 4 pi I by 5, e to the power 6 pi I by 5, and e to the power 10 pi I by 5. These are all the roots of this particular polynomial. They form a group under multiplication, and it's in fact a cyclic group. And e to the power 2 pi by 5 is one of the generators of this group. That is why we are calling it a primitive fifth root of unity, because it's a generator. We are calling it a primitive fifth root of unity, which means that no smaller power of e to the power 2 pi by 5, no power smaller than power 5 can give you 1. Okay, is it okay? I sort of didn't. Yeah. So let's move on to the next problem. Okay, so we need to figure out which of the following. So problem 2, which of the following extensions k over f are normal. So everyone is okay with what normal extensions are, right? What are normal extensions? I defined it just now, but just to reiterate, what is a normal extension? So an extension E over F is said to be a normal extension if it is an algebraic extension and every irreducible polynomial over the base field that has a root in the extension E, that is every irreducible polynomial over f that has a root in E, splits completely over E into a product of linear factors. That is, if you take any irreducible polynomial over the base field and if this polynomial has some root in the extension, then this polynomial will have all its roots in the extension. If this is true for every irreducible polynomial over the base field which has a root in the extension, then the extension E over f, the algebraic extension E over f, is called a normal extension. And there are various ways of classifying normal extensions as well. So one of the ways is to say that, so if your extension in addition to being just normal is also finite, then so a finite normal extension is precisely a splitting field of some polynomial over the base field. Okay. So there are various ways of characterizing normal extensions. So we just need to figure out which of these extensions are normal. So option A is K is Q adjoined with 4th root of 2 and F is Q. Option B is K is Q adjoined with 4th root of 2 and F is Q adjoined with root 2. Option C is K equal to Q adjoined with 4th root of 2 comma I and F is Q. And option D is K is C and F is R. We need to figure out which of these extensions are normal extensions. Right. So what about the first one? Is K over F? So is option A correct or false? So solution. What do you think? Option A should be correct or false? Why? Yeah, so A is indeed false, but you need to be careful about the reason. A is certainly not correct. Why? I didn't understand. Okay, let's just look at this particular polynomial. Consider x to the power 4 minus 2 in Qx. This is a perfectly well defined polynomial in Qx, and by Eisenstein, what can we say? That this, we can say that this polynomial is irreducible over Q, right? Right? Eisenstein does say that, right? Because you can just look at the prime 2, observe that 2 doesn't divide the leading coefficient, which is 1 in this case. 2 divides all other coefficients. There is only one other coefficient, namely the constant term minus 2. And further, 2 squared doesn't divide the last coefficient, the constant term, right? So indeed this polynomial is irreducible over Q by Eisenstein's criteria, and hence, and observe that the 4th root of 2, that is 2 to the power 1 over 4, is a root, right, of this polynomial. Yeah. Now we can in fact find out all the roots of this polynomial, right? Roots of this polynomial Q adjoined with roots of x to the power 4 minus 2 in Qx are the 4th root of 2 minus of the 4th root of 2, I times the 4th root of 2, and minus I times the 4th root of 2, right? Is it okay that these are all the these are all the four roots of this polynomial in C. Now it's very easy, right? Now Q adjoined with 2 to the power 1 by 4 doesn't contain I times 2 to the power I by 4, right? This root is not contained in this extension, is it? The complex roots don't lie in this extension, right? Not the rational field. They don't lie in this extension, right? Yes, since q adjoined with 2 to the power 1 by 4, this is contained in R, right? This is a subfield of R actually, right? It's fully contained in R. So it won't contain any complex roots, right? So what? So we have found an instance of a irreducible polynomial over the base field that has one root in your extension q adjoined with 2 to the power 1 by 4, namely 2 to the power 1 by 4 itself, but there are no other roots of this polynomial, right, contained in this particular extension, right? For it to be a normal extension, you need that for every irreducible polynomial over the base field that has a root in this extension, all its roots must be in this extension. But we have an irreducible polynomial over the base field, namely x to the power 4 minus 2, which has one root in this extension, but there are no other roots contained in this. I mean, not all roots are contained in this extension, right? This and this are not inside the extension. If we take, can you repeat? Then yes, that is our option D, right? So we need to check that. Yes, you are right. So hence this is not normal. Option A is incorrect. What about option B? Option B says that K is Q adjoined with fourth root of 2 and F is Q adjoined with square root of 2. So is K over F normal? No, no. Option B will be correct actually, because as you as I just said, right, that all splitting field, see, finite normal extensions are the same as splitting fields. Okay, so every finite normal extension is a splitting field of some polynomial over the base field. Okay, now proving that if the extension is finite and normal, then it's a splitting field of some polynomial over the base field is easy, but the opposite direction is a bit difficult. Okay, that is proving that if you have a splitting field of some polynomial over the base field, then this extension is a normal extension. Proving this is a bit difficult, but this is indeed true. Okay, so if an extension is indeed a splitting field of some polynomial over the base field, then that extension has to be a normal extension. Here this is what happens. So option B is correct. No, but why do you need to why do you need to go there, I into fourth root of 2? Why are you looking at that particular polynomial? Is x to the power 4 minus 2, is this, we know that this is a polynomial in qx, and hence this is also contained in our given base field in this situation, which is q adjoined with root 2 x. This is true, but to check for normality, you also need to make sure that the polynomial that you are looking at should be an irreducible polynomial, right, over the base field. Now this is irreducible over qx, that's okay. I mean over q, that's okay. We have seen using Eisenstein. But is x to the power 4 minus 2 irreducible over q adjoined with root 2x? I mean, is it irreducible in q adjoined with root 2x? That's certainly not true, right? Because you can because you can write this as x square plus root 2 times x square minus root 2, right? Root 2 is an element of q root 2, so you can this decomposition is valid, this decomposition into factors is valid in q root 2x, right? This is an element of q root 2x and this is an element of q root 2x, right? So certainly this polynomial breaks, you can break it like this, right, into two factors, which means that this polynomial can't be irreducible over q root 2x, right? It's reducible. So to check for normality, you can look at this particular polynomial. You need to make sure that every irreducible polynomial over the base field that has a root in the extension has all its. No, there are of course irreducible elements, but this is not what we this is not irreducible. X to the power 4 minus 2 is not irreducible. So since I am claiming that this is correct, that indeed this is a normal extension, what we need to check is that we need to show that this extension is a splitting field of some polynomial over the base field. Any polynomial over the any polynomial's splitting field will be a normal extension. Any polynomial. So let's just look at this particular polynomial. So consider the polynomial x square minus root 2 in Q root 2 x. Its roots are 2 to the power 1 by 4 and minus 2 to the power 1 by 4. Am I correct or wrong? Am I correct? Correct. Hence, what will be a splitting field of this polynomial over the base field Q root 2? It will be hence Q root 2 joined with this root 1 by 4. No, I doesn't come here, right? Because you are taking as a polynomial of degree 2. And root 2 is a minus root, I mean the root 2 is a positive real number. So it will have a square root, right? It will have a real square root. So hence what will be a splitting field by definition is an extension over which the given polynomial splits completely into a product of linear factors, and it is a minimal extension over which this happens, right? Which means that this extension is the base field adjoined with the roots. So the base field is Q root 2 and you adjoin with it the roots of this polynomial, right? What are the roots? 2 to the power 1 by 4 and minus 2 to the power 1 by 4. Now it doesn't matter which one of them you take, because if you just take 2 to the power 1 by 4, then minus 2 to the power 1 by 4 will automatically be contained in that extension. So this is just Q adjoined with 2 to the power 1 by 4. This is a splitting field. Of x square minus root 2 over the base field Q root 2. And since it's a splitting field, since Q adjoined with 2 to the power 1 by 4 is a splitting field of this polynomial over this base field, hence the extension Q 2 to the power 1 over 4 over Q root 2 is normal. So option B is certainly correct. Now what about option C? This you can answer easily. Is option C correct or wrong? So what you are doing is you are adjoining to Q 4th root of 2 and I. Okay, this is your extension and it's an extension, your base field is Q. So will this extension be a normal extension? Why? Yeah, but I has been included, right? So this extension contains I and 4th root of 2. Yeah, so what? This extension contains I and 4th root of 2, which means that it contains 4th root of 2 minus 4th root of 2, I times 4th root of 2 minus I times 4th root of 2. And we saw that x to the power 4 minus 2 is a polynomial in Q, right? I mean in Qx, right? So if you look at the polynomial again, so C is correct. If you look at the polynomial x to the power 4 minus 2 in Qx, if you look at this polynomial, what are its roots? We just wrote it in option A. So the roots of this polynomial in C are 2 to the power 1 by 4, 4th root of 2 minus 4th root of 2, I times 4th root of 2 and minus I times 4th root of 2, right? Hence a splitting field will be the splitting field of this polynomial over Q is Q adjoined with all these roots, right? So 2 to the power 1 by 4 minus 2 to the power 1 by 4, I times 2 to the power 1 by 4 minus I times 2 to the power 1 by 4. But this is the same as Q adjoined with 2 to the power 1 by 4 and I, right? Both these two fields are the same, right? If you take Q adjoined with 2 to the power 1 by 4 and I, then this particular field contains all these four fields, I mean all these four roots, and you know that the q adjoint with 2 to the power 1 by 4 minus 2 to the power 1 by 4 I times 2 to the power 1 by 4 and minus I times 2 to the power 1 by 4. This by definition is the smallest subfield of C which contains both q and all these four roots, which shows that since this contains q and the four roots, so this containment is 2. And conversely, if you look at this q adjoint with all these four roots, then this field, this subfield will contain both 2 to the power 1 by 4 and I, right? Because a field must be closed under division. So both of them should be in I, which means that it contains 2 to the power 1 by 4 and I, and hence it will contain q adjoint with 2 to the power 1 by 4 comma I, which is the smallest subfield of C containing both 2 to the power 1 by 4 I as well as q. So both inclusions are true, which means that they are equal. Right? This is very trivial, right? There is nothing wrong with this. Which means that indeed q adjoint with 2 to the power 1 by 4 comma I is a splitting field of some polynomial over q, and thus this extension is a normal extension. Is it clear, Ravi? If you guys have any questions, please feel free to ask. And what about option D? Yeah, so we come back to Ravi's question. Is C over R a normal extension or not? First of all, answer these questions for me. Is C over R finite? Is it a finite extension? Yeah, complex numbers over R, is it a finite extension? Okay, so why is it true? It is true. It is correct. Why is C over R finite? So C can be written as R adjoint with I, right? R adjoint with iota, right? Now R adjoint with iota over I is a finite extension because I is algebraic over R, right? What is the minimal polynomial of I over R? It's x square plus 1, right? X square plus 1 in Rx is an irreducible polynomial and I is a root of this polynomial, right? Which means that this I is algebraic over R, which means that the extension Ri over R has to be a finite extension, and in fact the degree of this extension is precisely 2. Okay, so Ri over R is a finite extension in particular, I mean therefore means that C over R is a finite extension because C is R adjoint with I. So it's a finite extension, hence an algebraic extension. We just need to figure out whether this is normal or not, right?
So the extension of complex over R will be finite.
Yes, it will be finite, but
Will be finite.
yes, but is it normal? See, you can do this in various ways. It will be normal, so D is correct. You can do it in various ways. First of all, C over R is indeed a splitting field of some polynomial over R, right? Which polynomial? We just mentioned it.
X square plus 1 equal to 0.
Yes, that's an equation, but if I am asking about the polynomial, you can just say x square plus 1. Yeah, so C over R is a splitting field. Of the polynomial x square plus 1 over R, right? It's a splitting field of this polynomial, which implies that C over R is normal. And another way in which you can deduce this is again easy. You know that C is algebraically closed, right? C is an algebraically closed field, right? Yes, it's an algebraically closed field, which means that every polynomial over C, non-constant polynomial over C, has a root in C, right? Now you take any irreducible polynomial over R, okay? Assume that this irreducible polynomial has a root in C, Okay, then this irreducible polynomial must have all its roots in C. Why? Precisely because this irreducible polynomial over R is also a polynomial polynomial over C, right? And you know, by since C is algebraically closed, every polynomial will have all its roots in C, right? Every polynomial over C, non-constant polynomial over C, will have all its roots in C. Okay, so it doesn't matter here whether the irreducible polynomial over R has a root, I mean whether you are assuming that this polynomial has a root or not, it will have all its roots in C. Okay, every irreducible polynomial over R will have all its roots in C. Okay, so vacuously you can say that it is normal, this extension is normal. Okay, because any irreducible polynomial over R which will have a root in C will have all its roots in C. That is, it will split completely into a product of linear factors over C. So it's trivially correct. So option D is correct. Okay. Oops. If you have any questions, please do ask. So let's discuss problem 3. Okay, so let's by the way, do you guys attend Ajay Prajapati's sessions? Do you attend his sessions? I mean, I think he solves the same problems, right? Yeah, that is why I need to change questions now, I think. Let me solve some other problem. Let's see. Okay, so let's do this one. Let's see, maybe this one we can do. So we need to choose all the correct options. Option A is x to the power 5 minus 1 is separable over f9. Do you know what f9 is? F9 is just the finite field of order 9. So up to isomorphism, there can be exactly one finite field of order p to the power m, where p is a prime and m is any positive integer. F9 here is a finite field of order 3 square. So option B says x to the power 5 minus 1 is separable over f5. Option C says x to the power 5 minus 1 is separable over f25. And option D says x to the power 5 minus 1 is separable over q. So what is a separable polynomial? Someone tell me. A polynomial px over a field f is said to be separable when? When do we say that a polynomial is separable?
All the roots are distinct.
Yes, yes, good. That is a polynomial, let's say fx over a field f is said to be separable if it has the polynomial has only simple roots. Okay, that is, all the roots of the polynomial are distinct. In other words, it has no multiple roots or it has no repeated roots. When I say it has distinct roots or it has no multiple roots or it has no repeated roots, what I am trying to mean is that it has not, it has, I mean, all its roots are distinct in some splitting field. Okay, right. I mean, that's clear, right? Yeah. All its roots are distinct in some, I mean, it has distinct roots in a splitting field, in any splitting field over the base field. Or in any extension over which the polynomial splits. So what is an equivalent way of checking for separability of a polynomial? Do you guys know this? What is an equivalent way for checking separability of a polynomial?
Find the factors of that polynomial.
Yeah, but that is not always possible, right? I mean, that's a hard problem. That's a problem that is hard to solve. Factorizing the polynomial is a hard problem, right? You can't always be sure what are the roots of this polynomial. But there is an easier way to do this, right? Do you guys, I'm sure you guys have also studied formal derivatives, right, of a polynomial? Taking the derivative of a polynomial, right?
Yes. Derivative of polynomials.
And a polynomial fx is separable if and only if. When do we say that it is separable?
The derivative is 0 or not.
No. Polynomial is separable if and only if the GCD of fx and its derivative is exactly 1.
मतलब they are co-prime.
Yes, fx and its formal derivative should be relatively prime. If that is the case, then this is equivalent to saying that the polynomial fx is separable. That is, fx has no repeated roots in any extension over which it factors fully. That is, the polynomial has only simple roots. Saying that some polynomial is separable over a given field actually is only something dependent on that field. Okay, it doesn't depend on any extension. I mean, what I'm trying to say is, suppose you take a base field f, you take a polynomial over the base field, and you have you are taking two splitting fields, okay, both of which are extensions of the base field. You take two splitting fields of this particular polynomial over the base field. It's not the case that it could happen that this polynomial fx has distinct roots in one splitting field, but some of its roots are repeated in the other splitting field. That can't happen. A polynomial, so if fx factors like this in some extension, let's say fx factors like this, x minus a1 power m1, x minus a2 power m2, dot dot dot, x minus ak power mk. Suppose it factors in omega 1 x like this, and suppose fx factors like this, let's say a times x minus b1 power n1, x minus b2 power n2, dot dot dot, x minus ar power nr in omega 2x. Okay, if I mean, this can't have, I mean, what I'm trying to say is the factorization has to be the same. Okay, so what I mean by this is that firstly k has to be r, and secondly a1, I mean, what I'm trying to say is, how should I say this? Yeah, also assume something more, that m1, you have rearranged the factors in a way that m1 less than equal to m2 less than equal to up to mk, and here you have rearranged the factors such that n1 less than equal to n2 dot 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 less than equal to nr. Okay, now if fx has these two different factorizations in omega 1x and omega 2x respectively, then k has to be equal to r, and moreover m1 has to be equal to n1, m2 has to be equal to n2, dot dot dot, mr has to be equal to nr. Okay, this has to be true. That is, in other words, this increasing sequence m1, m2 dot 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 mk of powers of the respective factors, this increasing sequence should be invariant. Okay, regardless of whether you look it in omega 1 or you look at it in omega 2, this sequence will be the same. Sequence of powers will be the same. Okay, so in particular, if the polynomial is separable, then all these powers have to be 1, right? Because it, as you said, Ravi, it has no distinct, I mean, all its roots are distinct. So all powers will be 1, and this is true over any splitting field. Okay, so that is why a polynomial separability of a polynomial is a well-defined concept. A polynomial over a given field is separable means that it has same factorization into I mean, it factorizes into distinct linear factors over any splitting field. Yeah, so you were saying something, Ravi. Yes, that is one other way of checking whether a polynomial is separable or not. There is another way as well. There is something called the discriminant of a polynomial, right? Yeah. I didn't understand. Maximal what? Yeah. No, that's it. That is, I guess you are referring to Bezo's theorem, right? Which says that in a in general, which says that in a Euclidean domain, if two elements A and B are relatively prime, in fact, we can say something in further generality that the ideal joint by A and B will be equal to the ideal joint by their GCD, which means that the GCD can be represented as a linear combination of A and B. Is this what you are referring to? I didn't understand where maximality comes in the picture, but anyways, so let's solve this problem. So yeah, so as I was saying, there is a further way of checking this, whether a polynomial is separable or not. You can also define something called the discriminant of a polynomial. So if you take a polynomial fx in capital Fx, assume that this polynomial has a splitting field E over F, then you will define something called the discriminant of this polynomial, which is uh, which is the product of, so suppose the roots of this polynomial are alpha 1 up to alpha n in the splitting field, then you take the product over I less than j, alpha I minus alpha j. Okay, and you define the discriminant of this polynomial df to be equal to delta square, the square of this polynomial. Now certainly if the polynomial is not separable, then it will have repeated roots, which means that this product has to be equal to, if two roots are equal, then this product becomes,
If two roots are equal,
let's say,
square.
no, if two roots alpha 1 and let's say alpha I and alpha j for some I and j are equal.
Separable.
Yeah, that's true, but what happens to delta f? What does delta f become in that case? It's easy, right? Alpha I minus alpha j for some I and j are equal. Yes, this will become 0, right? So if the polynomial is not separable, then the discriminant is 0, and conversely if the discriminant is 0, then the polynomial cannot be separable, right? So another way to check that a polynomial is separable over a field is just to check that its discriminant is non-zero. You can prove that that df, this df that we are talking about, this df will be in the base field capital F. This will be an element of capital F. Yeah, we are taking I mean fields of characteristic 0 and all those things we are taking here, but yeah, you can prove that df is indeed 0. Okay, so let's solve this problem. So I need to choose all the correct options here. So x to the power 5 minus 1 is separable over f9 or not? Yes.
This is same. The problem one also same polynomial. So we'll factorize it.
Yeah, but there the extension was over q, right? Here we have taken over f9. Option A is over f9, the field with 9 elements. Okay. Okay. So yeah, but we do have that criteria, right? We can look for the GCD. So what is the GC, what is the derivative, formal derivative of, so let's call, so let's take, so let's take fx equal to x to the power 5 minus 1. What is f prime x? Yeah, 5x to the power 4 is the derivative. Now over, we are doing this over f9, right? What is the GCD of x to the power 5 minus 1 and 5x to the power 4 over f9? What is this? Okay, why is it 1? Yes, I agree this is 1, but why is it 1? Okay, tell me something. Suppose you take a polynomial fx and you take another polynomial gx, and suppose that they are GCD. So suppose f and g, fx and gx are polynomials over some base field f, and suppose that the GCD of fx and gx is not 1. Okay. Then can we say that both these polynomials will have a common root in some splitting field? In some splitting field, right? So check that two polynomials are relatively prime, we can just work in the contrapositive direction and say that, and try to see whether these two polynomials have a common root or not, right? So tell me, what are the roots of this polynomial 5x to the power 4 over f9? What are the roots of this polynomial over f9? This is a non-zero polynomial, right? What are the roots of this polynomial? It's easy, right? 5x to the power 4. What are the roots of this polynomial? What is there to think in this? 5 times x to the power 4. What are the roots of this polynomial? Suppose alpha is a root of this polynomial, then 5 alpha to the power 4 is 0, right? Which implies alpha is 0 because you are working in an integral domain. So the only roots of this polynomial is 0, right? 0 is the, I mean 0 has multiplicity 4. And what about x to the power 5 minus 1? Is 0 a root of that? Certainly not, right? So the GCD has to be 1, which implies that fx is separable over f9. That is, fx belonging to f9x is a separable polynomial. That is, this polynomial has only simple roots, or all its roots are distinct, or over any splitting field it has exactly n distinct roots, where n is the degree of this polynomial. It has no repeated roots, it has no multiple roots, it's the same thing. What about option B? Is x to the power 5 minus 1 separable over f5 or not? So again take fx equal to 5 minus 1 in f5x. So what happens to f prime x? Yes, but the base field is f5, right? What is special about f5? f5 has characteristic 5, right? Which means that 5 times 1 is 0, right, in f5? So what happens? No, but what can we say? No, 5 times 1 is 0, right? Which implies 5x to the power 4. This polynomial is a 0 polynomial, right? Isn't it? And then GCD of fx and f prime x, what is that? This is equal to, no, 0 can't be the GCD. The GCD here is x to the power 5 minus 1. 0 can be the greatest common divisor, right? 0 is not even a divisor, right?
Yes, zero computer.
So the point is the GCD is x to the power 5 minus 1, which is certainly not equal to 1. Hence, fx is not separable, right? Okay, so take an element A in a ring, take 0 in the ring. What is the greatest common divisor of these two elements by definition? It is an element which is a divisor of both and which is divisible by every common divisor, right? Now take D to be the greatest common divisor of A and 0. Then D divides A and D divides 0, right? Which means that A has to be the greatest common divisor, right? A has to be equal to D. Isn't it? The greatest common divisor of one element and 0 has to be the non-zero element, right?
Yes, sir.
Yeah, alternatively you can do this like this. I think Ravi, you are suggesting something. You are suggesting this only, that you can write this polynomial x to the power 5 minus 1 over f5 as x minus 1 power 5, right? Why? Because the characteristic is 5. If you just expand this using the binomial theorem, this becomes 5c0 x to the power 5 minus 5c1 x to the power 4 plus 5c2
Plus 5
x cube, and whatever the coefficients are. The point is that this is divisible by 5, so it will be 0. This is divisible by 5, this will be 0, and ultimately the only non-zero term left will be minus 1 and the first term. So this is x to the power 5 minus 1, right? Over any field of characteristic P, that is if you take if you take any field f of characteristic P, then this map from f to f sending a to the power p, this particular mapping is called the Frobenius endomorphism. Okay, this is a group this is a field homomorphism, you can check. This is certainly multiplicative, that is easy, precisely because f is commutative, but it also preserves addition or commutes with addition, because a plus b whole to the power p is a to the power p plus b to the power p, precisely because the field has characteristic p. So all the intermediate coefficients in the binomial expansion will become 0. Every intermediate coefficient is divisible by p, so it will become 0, and you are only left with a to the power p plus b to the power p, which shows that this map is a homomorphism, field homomorphism. This is called the Frobenius map or the Frobenius endomorphism of the field f. Okay, so the same thing happens here actually. The field f5 has characteristic 5, and hence x to the power 5 minus 1 is just x minus 1 power 5. Anyways, the point that I'm trying to make here is this, that x minus 1 power 5, is this polynomial a separable polynomial? So x minus 1 power 5, what are the roots of this polynomial? The roots of this polynomial are 1, 1, 1, 1, 1, 5 times. So it has repeated roots, right? 1 is a root of multiplicity 5, which means that the polynomial cannot be separable, right? Yeah. The polynomial can't be separable. Yeah, so option B is not correct. Option A is correct. Option C is again incorrect, precisely because F25, which is a field with 5 square elements, that is 25 elements, this also has characteristic 5, right? Isn't it? F25 has characteristic 5, again the same argument works, and option D is again correct. That is x to the power 5 is x to the power 5 minus 1 is indeed separable over Q. So C is incorrect. Correct. Same reason as B. And what about D? D is correct. D is correct. Sorry. Yeah. D is correct, as x to the power 5 minus 1 in qx is a separable polynomial. Why is it separable? As the roots of this polynomial in C are the fifth roots of unity, right? Are 1 e to the power 2 pi I by 5, e to the power 4 pi I by 5, e to the power 6 pi I by 5, e to the power 8 pi I by 5, all of which are distinct. Okay. And alternatively, what you can do is you can use the GCD test. Use the GCD criteria. So the formal derivative of this polynomial will be 5x to the power 4, right? And that has to be relatively prime to x to the power 5 minus 1. Either you can use the division algorithm. You could have used the division algorithm even in option A as well. Instead of checking that 0 is a root of one polynomial and 0 is not a root of the other polynomial, you could have just used the division algorithm, showed that, I mean, explicitly computed the GCD to be 1. You could have done that as well. Here also you can use the division algorithm, explicitly show that the GCD is 1, that is keep on dividing the Euclidean. Yeah, you use the Euclidean algorithm, you keep on dividing. So A is equal to BQ plus R, then use the remainder and divide it, I mean divide the B. So step 1 is A is equal to BQ plus R. Step 2 is write B, I mean divide B by the remainder R of the previous step. Whatever remainder you get, you keep on doing this process and ultimately you'll arrive at the GCD. Okay. Yeah. So you can use that, or you can directly show that as usual 5x to the power 4 has 0 as a root, but 0 is not a root of x to the power 5 minus 1, which means that these two polynomials have to be relatively prime. Okay, because if they were not relatively prime, then in some splitting field of both, I mean over some extension where both these polynomials split, they should have a common root. Okay, or they should have a common factor, you can say. The polynomial should have a common factor and hence a common root, but they don't have a common root because 0 is the only root of the derivative, while 0 is not a root of x to the power 5 minus 1. Okay, so yeah, option D is correct as well. So let's move on to another problem. Problem 5 maybe, or 4. Yeah, I wasn't very prepared today. I sort of forgot that I had to take your class, and suddenly all of a sudden at 5:45 I got reminded, so I didn't write questions today. Let's see which one we can solve. So you guys have studied Galois extensions this week? Can someone let me know if you have studied Galois extensions this week? Someone maybe. You guys don't attend classes or don't see the videos, uploaded videos of the lectures? Say something. Yeah, so did you study Galois extensions this week? No, where you taught Galois extensions this week. So you guys were taught normal extensions, separable extensions. Did you also study Galois extensions? Yeah, okay. So let's see this. So let K be the algebraic closure of Q, then K over Q is a Galois extension. Is this true or false? So you need to figure out whether this statement is true or false. Okay, so why is it true? Yeah, why? That is what I'm asking. You are just repeating the question. K has been taken to be the algebraic closure of Q. What do you mean by algebraic closure? By definition, an algebraic closure of a field is an algebraic extension of the field such that every polynomial over the base field has, splits completely into a product of linear factors over this extension. Right? This is what we mean by algebraic closure. That is, this is what the purpose of studying field theory is, right? You want to find a field which contains all roots. You find, so given a field you want to find, so given a field you have polynomials over the field, and it could happen that loads of polynomials don't have roots in this field. So what you want to do is you look at splitting fields of this polynomial, splitting field of this polynomial, splitting field of that polynomial over the base field. But you need to find a common field which contains all roots of all polynomials over the given field, right? And that common field is, should you choose to assume that this extension is algebraic, that common field is called the algebraic closure precisely. Okay, so it's an algebraic extension of the base field such that every polynomial over the base field, every non-constant polynomial over the base field has all its roots in this extension, or splits completely into a product of linear factors in this extension. Okay, this is what we mean by algebraic closure. And the algebraic closure of Q in C is precisely the field of all algebraic numbers, numbers which you define to be algebraic, right? That is all complex numbers which satisfy a non-zero polynomial equation over Q. Those are called algebraic numbers, and the algebraic closure of Q is this collection of algebraic numbers. So let K be the algebraic closure of Q. You need to figure out whether K over Q is a Galois extension. Now there are various ways of defining Galois extensions. I'm sure you have seen all of them. One of the ways is to define it like this, that it's an algebraic normal and separable extension. Okay. Now Q is a field of characteristic 0, which means that it's a perfect field, right? So what do I mean by perfect field? Perfect field means that every algebraic extension of this field should be separable. Okay, so Q being of characteristic 0, is perfect. I'm sure you have seen perfect fields. If in case you have problems, you can ask me. So Q being of algebraic, being of characteristic 0 is perfect, and hence K over Q being an algebraic extension is separable. So a field is called perfect if and only if there are many equivalent statements. One of the statements says that every irreducible polynomial over this field is separable, or you can say that every finite extension of this field is separable, or you can say that every algebraic extension of this field is separable, or you can say that let's say the field is either of characteristic 0 or it has characteristic P. And the Frobenius endomorphism that I have been describing you, this Frobenius endomorphism is actually an automorphism. That is, it's a bijection, it's an isomorphism of F onto F. Okay, and there are many other equivalent statements as well, but the statements that you will be using the most, the statement that you'll be using the most will be this one, that a field f is called perfect if and only if every irreducible polynomial over the field is separable. Any irreducible polynomial over the field you take, that has to be separable. Okay, so these are some of the equivalent ways of saying. So now Q being of characteristic 0 is perfect, and hence K over Q being algebraic is a separable extension. So we are only left to see whether this extension is a normal extension or not. Indeed, it will be normal as well very easily, because as so let Px in Qx. So certainly this extension is algebraic. Now let Px in Qx be an irreducible polynomial. Polynomial over the base field, and let alpha be a root of Px in the extension K. Okay, then Px has all its roots in this extension. Then Px, you need to check this, right? To check for normality, you need to show that Px must have all its roots in the extension. Now observe that Px has been taken to be an irreducible polynomial. It has been taken to be some non-constant polynomial over the base field, and since K is an algebraic closure of the base field, hence this polynomial will split completely into a product of linear factors, right, over this extension by definition of algebraic closures. So then Px has all its roots in the extension K, as K is equal to the algebraic closure of Q, that is K is equal to Q bar, right? So it doesn't matter whether Px has, it doesn't matter whether you assume that Px has a root in K or not. Regardless of that, Px will always have all its roots in K. Okay, so in this particular instance where you have assumed that Px has a root in K, Px does have all its roots in K. So indeed this is a normal extension. Thus K over Q is normal. Hence K over Q is a Galois extension, because it's algebraic, normal and separable, so it's Galois. Okay, so let's see the next problem. Yeah, if you have a question you can ask me. Please feel free to ask. So problem 5, let K denote the algebraic closure of Fp where P is a prime. Then K over Fp is a Galois extension. Yeah, so will this be true or not? Someone, oh, only you are here. Yeah, so will this be correct or not? What do you think? This will be correct. Okay, why? So to check that this is a Galois extension or not, what you need to figure out is that this is a algebraic extension, separable extension, as well as a normal extension, right? Yeah, so first of all, is this algebraic? No, first of all, let's go step by step. Is this algebraic or not? By definition, this is algebraic because K over Fp is the algebraic closure, so it is algebraic by definition. Now, is it separable or not? Yeah, it will be separable. precisely again because fp is a finite field, hence finite field has to be perfect, which means that any algebraic extension of it has to be a separable extension. Okay, so so fp is certainly separable. And finally, what about normality? What again, it will be normal, right? Whatever argument that we gave for the normality of the algebraic closure of q, the same argument holds here, right? So same as above. So this is true, so this is again true, and the reason is same as above, as you were saying. Just note something here, that since fp is finite field, hence the map, the Frobenius endomorphism, a going to a power p of fp into itself is an automorphism, so that fp is perfect, and hence k over fp is separable. Yeah, so what I wrote here is simply this, that you have this Frobenius endomorphism of fp into itself, right, where a goes to a power p. This is a field homomorphism, so in particular it's injective, there's nothing wrong with this. So it's a monomorphism, you can say. Now to check that it's an automorphism, you need to show that this is an isomorphism. So the only thing left to check is to see whether this map is surjective or not, right? Now since it's a finite field, since fp has p elements precisely, so if you take a mapping of one finite set into itself which is injective, then can you say that it's automatically surjective? Did you understand the question? So suppose S is a finite set with, let's say, n elements, and you take a mapping of S into S, okay, S into itself, and you are given that this map is injective, then can you say that this map will be surjective as well? It's easy, right?
Yes, sir.
Since it's injective, image will have exactly n elements. The image is a subset of the codomain or the target which has n elements. That means that the image is exactly equal to the codomain, right? So the map has to be surjective. And conversely, you can see that if the map were assumed to be surjective, then it will be injective. Okay. This is precisely something called the pigeonhole principle. So anyways, that argument works here, since the mapping of fp into itself is always an injection, and fp here is a finite field, and hence in particular the underlying set is finite. So this mapping which is injective has to be surjective, so that this Frobenius endomorphism has to be bijective, that is, it has to be an automorphism of fp. And since it's an automorphism, the field fp is a perfect field, so that any algebraic extension of it has to be separable. So in particular, k over fp is a Galois, is a separable extension, and hence a Galois extension. I don't know what just happened. Yeah. Yeah, so the reason is the same as before. So let's solve one problem. So problem 6. Let's see, we need to choose all the correct options here. Choose all the correct options. Option A says splitting field K of the polynomial 2x to the power 4 plus x cube plus 5 in Qx is a Galois extension. Option B says f5 adjoined with t over f5 adjoined with t square is a Galois extension. Option C says q adjoined with I and fourth root of 2 over q adjoined with I is a Galois extension. Option D says f5 adjoined with t over f5 is Galois. Okay, so which of these will be correct? Yeah, which of these will be correct? Is statement A correct or not? Splitting field of this polynomial in Qx is a Galois extension. Yeah, A is correct. Why? Why is A correct? So observe that the splitting field K of this polynomial over Q, it is a finite extension, right? Always. Splitting field of any polynomial is a finite extension of the base field, right? Yeah, that's true, right? Because you know that the splitting field is, the degree of the splitting field is bounded by n factorial, where n is the degree of the polynomial, right? So splitting field of any polynomial over a base field is a finite extension, and hence, since it's a finite extension, hence it will be separable because Q has characteristic 0, so Q is a perfect field, right? So this extension is certainly separable, and splitting fields are normal, right? And hence your turn. A is correct, as K over Q is separable, normal. It is both separable as well as normal, right? And hence in particular algebraic as well. So this is a Galois extension. What about statement B? F5 adjoined with T over F5 adjoined with T square is a Galois extension or not? Okay, so just look at the polynomial x square minus t square in f5 t square. This is a polynomial in f5 t square, you agree, right? I mean f5 t square x, you agree, right? Now this polynomial, what are the roots of this polynomial? The roots are t and minus t, right? And t is certainly not equal to minus t. T is not equal to minus t as characteristic of f5 is not equal to 2. The characteristic of f5 is precisely 5, so t cannot be equal to t, because otherwise if t were equal to minus t, then 2t would be equal to 0, right? Which would mean that the characteristic of f5 is 2. The characteristic of f5 is 5, not equal to 2. So this polynomial has two distinct roots, right? It has two distinct roots in f5 t or in any extension, which means that this polynomial is certainly a separable polynomial, right? And what is a splitting field of this polynomial over the base field? So a splitting field is splitting field over the base field f5 t square. Sorry, let me write it properly. Yeah, splitting field over this base field is f5 t square adjoined with t, adjoined with the roots t and minus t, which is equal to f5 t. So f5 t is indeed the splitting field of some separable polynomial over the base field, right? And that is an alternate definition of defining a finite Galois extension, right? That an extension is finite Galois if E over F is a finite Galois extension, if and only if E over F or E is a splitting field of some separable polynomial over F. So you indeed found a separable polynomial over the base field which has this extension f5t as a splitting field. So f5t is indeed a splitting field of some separable polynomial over the base field f5t square. Okay, so the polynomial is separable as we just saw because it has distinct roots, and it is a splitting field over f5t square of some polynomial over f5t square, which implies that f5t over f5t square is a Galois extension. It is in fact a finite Galois extension. Okay, so B is correct. A is correct as well. What about option C? Is C correct? So why is C correct?
I and two also.
No, so can you find a separable polynomial over the base field which has this particular extension as a splitting field? We indeed saw this, right? A few minutes back when we were solving some problem, we saw that the polynomial x to the power 4 minus 2 in Qx is irreducible and hence separable because Q is a perfect field. So every irreducible polynomial over Q will be separable, is irreducible and hence separable, and has Q adjoined with I and fourth root of 2, sorry, fourth root of 2, yeah, as a splitting field over Q. Hence Q adjoined with I fourth root of 2 being the splitting field of a being the splitting field of a separable polynomial over Q is a Galois extension. That is an it's a finite Galois extension. That is an alternate definition of a finite Galois extension, right? So either you can define it to be there are many statements, but either you can define it to be, I mean, two most important ones are this, that either you can define it to be a finite normal separable extension, or you can define it to be the splitting field of some separable polynomial over the base field, or you can also define it to be you can also say that if you look at the Galois group of this extension, then the fixed field of the Galois group in the extension is precisely equal to the base field. Okay, and lots and loads of other equivalent ways of defining the same thing. Okay, so C is certainly correct. And what about option D? Is f5 adjoined with some t over f5 Galois? So t here is an indeterminate. Okay, so f5t is just the field of fractions of f5t. That is, if you look at the one variable polynomial ring over f5 and you sort of look at its field of fractions, then you get f5 first bracket t. So is this Galois over f5? Is this Galois over f5? Is F5 adjoint with T over F5 Galois? So for some extension to be a Galois extension, it in particular has to be an algebraic extension, right? So can T be, I mean, is it true that T satisfies some non-zero polynomial over F5? T is just a symbol. Okay. Can T satisfy some non-zero polynomial over F5? Which polynomial does it satisfy? It can't, right? T is just a symbol. You can think of T as X. Is there a polynomial over F5 which has X as a root? That's not possible, right? So D is not correct. Not correct. As F5 adjoint with T over F5 is not algebraic. This is not an algebraic extension. This is a transcendental extension. You in particular have found out an element which is not algebraic over F5, namely the element T. Because assume that T satisfies some polynomial over F5. Let's say P of T is equal to 0. That is, suppose a0 t to the power n plus a1 t to the power n minus 1 plus dot 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 plus an is equal to 0, where a0 up to an are elements of F5. Can this happen? This can never happen, right? Right? T is just a formal symbol, right? It's just a letter, right? This can't happen, right? Because a polynomial, I mean, this, you can think of this as an element in F5T, and a polynomial is 0 means that all the coefficients have to be 0, but we have chosen that at least one of the coefficients has to be non-zero, right? We assume that T is algebraic over F5, so it satisfies a non-zero polynomial over F5, and we indeed saw that we get a contradiction, right? Yeah, you had a question? So this is not Galois. So option D is incorrect. And all the other options are correct. So let's solve one more problem. Okay, so okay, let me ask a question of my own. Let's see. Okay, so let's see this. Let omega be the collection of all finite extensions of Q. You look at the collection of all finite extensions of Q. That is, in other words, you look at all the extension fields of Q which considered as a vector space over Q are finite dimensional. Okay, that is, the degree of the extension over Q is finite. So you look at the collection of all finite extensions of Q, and you obviously have a map. There is an obvious map, right? That is a degree map which maps omega into the natural numbers, which sends any E over Q, any extension E of Q onto the degree of E over Q. This is a well-defined mapping of omega into n, we agree. So my question is, this map is surjective. True or false? Is the question clear? It's very easy. So we have the collection of all finite extensions of Q, and we take a mapping of this collection into N, which sends every element in this collection, that is every extension E of Q, onto the degree of E over Q. This is a well-defined mapping of omega into N. The question is whether this map is surjective or not. Is this surjective? So what do I mean by surjective? So what I mean is that you take regardless of, so if you take any element of N, there has to be some element in omega which is getting mapped onto this element of N, right? That is what surjective means, right? Yeah. Onto plus into, what does that mean? Ravi? What is onto plus into? What is into? You need to say just onto, right? Isn't it? Surjective means onto. Yeah. Yeah, so is this surjective or not? So take any natural number in N. Can you find an element in omega? So you take, so think about this. You take any natural number in N. Can you find some element of omega which is getting mapped onto that natural number? Can you find some element in omega which is getting mapped onto that natural number? So let's take so solution, take any n in N. You need to come up with an extension of Q, a finite extension of Q, whose degree over Q is exactly N, right? This is what you have to do. So can you find an extension? Yeah. Can you find an extension of Q which is finite and whose degree is exactly N? So it will be correct. Take any natural numbers. Take Q adjoined with 2 to the power 1 over N over Q. This is a finite extension of Q, right? What is the degree of this extension? First of all, what is the minimal polynomial of 2 to the power 1 over N over Q? Ravi, what is the polynomial? What is the minimal polynomial? You look at this polynomial, x to the power n minus 2 in Qx. This polynomial is again irreducible. Why? Why is it irreducible? Why is it irreducible over Q? Just one line answer or one word answer rather.
Non-zero polynomial.
No, every non-zero polynomial over Q will be irreducible. Of course not. You can take the polynomial x minus 2 times x plus 2, right? That is not irreducible. Irreducible means that you cannot break it up non-trivially. That is, you cannot write it down as a product of two non-units or two polynomials of smaller degrees over the given field. That is what it means to be irreducible. Yeah, so Ravi, why is this irreducible over Q? We have seen this, right? Excuse me. This is true by Eisenstein. Hence, x to the power n minus 2 in Qx is the minimal polynomial. Of 2 to the power 1 over n. Because 2 to the power 1 over n is in particular a root of this polynomial, and this polynomial is monic and irreducible over Q. Thus, Q adjoined with 2 to the power 1 over n Q. The degree is exactly n. The degree of the minimal polynomial, which is n. So that the map is surjective. The degree map is surjective. Okay. So a question for you to ponder on after this. Bonus question. Is the degree map surjective? If you replace Q by some other field. Okay, so this is what you think about later, and maybe we can do one more question before we stop. Yeah. Let's see which one. So question 8, I guess. Yeah. So choose the correct options. Statement A is Q adjoined with e to the power 2 pi I by 5 or 9 over Q is separable. So is option A correct? You guys think about this. Let me write option B, but is option A correct? Is option A correct? Anyone? 9th root of 2. No, 9th root of 1. E to the power 2 pi I by 5 is the 9th root of 1. Yes. So is this a separable extension? Ravi, is this separable? Quickly, is Q adjoined with the 9th root of 1 a separable extension? This is called the 9th cyclotomic extension, right? You are adjoining to Q the ninth root of 1, the primitive ninth root of 1. Yeah, the polynomial will be x to the power 9 minus 1. This will be the polynomial which has this element as a root. And if you are looking at the cyclotomic polynomial, that is, if you are looking at the minimal polynomial, then that you can obtain that inductively. Okay, so let me just write down the factors. It will be x minus e to the power 2 pi I k by 9, where GCD of k comma 9 is equal to 1 and k is between 1 and 9. K is between 1 and 9, and the GCD of k comma 9 has to be equal to 1. Okay, or you can take k between 0 and 8 as well. Sorry, there's no point in taking k to be 0. You need to take k between 1 and 9. Yeah, and the GCD of k comma 9 should be equal to 1. That is, you just look at all the primitive roots and you take x minus and you include that as a factor. If you multiply it out, you can write down the cyclotomic polynomial. It will have degree exactly phi of 9, but phi is the Euler's phi function. So I guess that will be 6, I believe. Sorry. Yeah. So you don't need to write the polynomial for this. The point is that you have adjoined with q a primitive ninth root of unity, right? Which as you know satisfies some polynomial over q. So this extension has to be an algebraic extension. Sorry, excuse me. Yeah, so this extension has to be an algebraic extension. In particular, it has to be an algebraic extension, and in fact it has to be a finite extension, right? Because e to the power 1 to e to the power 2 pi I by 9, this is algebraic over q. It satisfies some non-zero polynomial over q, right? It is a root of some non-zero polynomial over q, so it is algebraic. So this extension is finite, and since q is a field of characteristic 0, hence any finite extension has to be separable, right? It's a perfect field. Q is a perfect field, so any algebraic extension will be separable. So indeed this extension will be separable. Yeah, so A is correct. Q is a perfect field. As Q is a perfect field, so A is correct. What about option B? F5 adjoined with T over F5 is separable or not? This is again not correct because of the same reason that we saw in maybe 2 questions back, that F5T. So this is not correct, because to have the, so what is a separable extension? So you know what separable polynomials over a given field are. A polynomial over a given field is said to be a separable polynomial if it has distinct roots, right? That is, it has only simple roots. And now if you take a field and an extension of the field, and if you take an element in the extension, then that element is said to be separable over the base field if it is algebraic over the base field, and its minimal polynomial over the base field is a separable polynomial. And finally you define an extension of a given field to be a separable extension if and only if every element in the extension is separable over the base field, right? So in particular, this means that a separable extension has to be an algebraic extension, right? Right? So B cannot be correct, as F5 adjoined with T over F5 is not algebraic. So B is incorrect. This cannot be separable, because regardless of whatever extensions you have seen, I mean separable extensions or normal extensions, whatever you have defined so far, yeah, because we just saw that T cannot satisfy T is a symbol, right? T cannot satisfy a polynomial over F5. It's an indeterminate, right? If T satisfies a polynomial over F5, let's say a0 t to the power n plus dot plus an is equal to 0, this is in f5t, right? This will imply that all the coefficients have to be 0, right? And that would mean that t is not algebraic, right? So t cannot satisfy a non-zero polynomial over f5, which is why it is not algebraic over f5. Okay. Okay, Ravi. Yeah, so certainly f5t over f5 is not separable, right? Because normal extensions or separable extensions, whatever extensions you study, you always assume that they are algebraic extensions first of all. Okay, so yeah. Now what about option C? Option C is correct. As, why is option C correct? As Q adjoined with fourth root of 3 comma I is the splitting field of x to the power 2 plus square root of 3 belonging to Q square root of 3, right? No, I think I am wrong. This is not the splitting field. The splitting field will be fourth root of 3 comma, I mean fourth root of 3 times I. Yeah, not comma I. But anyways, that also doesn't matter. The point is that this is a finite extension of Q root 3. So is a finite extension of Q adjoined with root 3, and Q adjoined with root 3 is perfect, being of characteristic 0. So why is this a finite extension? Again, easy to see. For you can use the Tower theorem. Okay, so Q adjoined with fourth root of 3 comma I is an extension. So yeah, so Q adjoined with fourth root of 3 comma I is an extension of Qi, and this is an extension of Q. Now certainly this is finite. Qi over Q is finite, and Q adjoined with fourth root of 3 comma I over Qi is again finite, because Q adjoined with fourth root of 3 satisfies a polynomial over Qi, right? Fourth root of 3 does satisfy a non-zero polynomial over Qi. So certainly fourth root of 3 is algebraic over Qi, so that this extension is a finite extension of Qi. And you can now use the Tower theorem to conclude that Q adjoined with fourth root of 3 comma I is algebraic over Q. And finally, so certainly C is correct. This is separable. Every finite, or in fact every algebraic extension of a perfect field is separable. Yeah, so what was option D? Option D, yeah, whether f at f3t is perfect or not. Yeah, so maybe you can try this before we stop. Is f3 adjoined with t perfect field or not? What do you think? Okay, why is it not perfect? Think about this for a while. Why is this not perfect? Can you find an irreducible polynomial over f3t which is not separable? Try to think. Huh? No, what do you mean by irreducibility of a field? That doesn't make sense, right? Irreducibility only applies to a polynomial, right? So do check this, check that. Okay, so this D will be not correct. To see this, check that x cube minus t is is certainly irreducible over f3 t, but not separable. To check that it is not separable is very easy. Okay, so to do this you can just look at x cube minus t polynomial, and you take an extension of this polynomial which contains a root of this polynomial, let's say alpha. Then in that extension, since alpha is a root of this polynomial, so you get alpha cube equal to t, right? And thus x cube minus t can be written as x cube minus alpha cube, which is x minus alpha whole cube, because the characteristic of f3t is 3 precisely. So you can write this polynomial as x minus alpha whole cube, which means that this polynomial, the roots of this polynomial are alpha, 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 which means that the polynomial has repeated roots, which means that the polynomial cannot be separable. The polynomial x cube minus t doesn't have all roots distinct, it has multiple roots, or it has repeated roots. Okay, this polynomial x cube minus t does have repeated roots, which means that the polynomial cannot be a separable polynomial. Okay, but do check that this is irreducible. So D is certainly not correct. Yeah, I guess we can stop here. If you have any questions you can ask, otherwise we can stop the session. Okay, then see you. Yeah, yeah.